Welcome back to Calculus 2, Section 6.2, Properties of Power Series. There's a number of topics to go over. 6.1, we introduced the notion of a power series. Here we want to talk about properties of power series. So in other words, what can we do with power series? We'll start off by combining power series. Let's get started. All right, so back in the previous video, we introduced the notion of a power series, and we relied heavily on a geometric series. If you recall, on a geometric series, for a convergent geometric series, where the very first term is 1 and the common ratio is r, you evaluate the geometric series as 1 over 1 minus r. So, and the r's in absolutes need to be less than 1, strictly less than 1. So by doing a simple swap, a change of variable from r to x, we can come up with this function f, algebraically given by 1 over 1 minus x, has a power series representation of the given form. Good. For g, the only difference on g is that the denominator is a sum rather than a difference. To express this sum as a difference, we can write down 1 minus negative x and be equivalent to 1 plus x. Thus, in the geometric form, we would, instead of swapping out x for r, we would swap out for r, we would swap out negative x. Plugging in a negative x for x, and then using properties of exponents, we can write the summands as a negative 1 to the n, product x to the n. Same notion occurs on the h, except this time we'll be swapping out negative x to the power 2. And then also the term appearing in the numerator, we treat that as the very first term, or a. And thus we're going to have negative 1 to the n, x to the 2n, the 2 coming from this denominator, and the plus 3 coming from this x to the power 3 in the numerator. All right, so we have functions that can be expressed as power series thanks to the geometric series. Well, we know that given a function f and given a function g, we can combine the two functions to get a sum function. We can take the difference of two functions, get a difference function, i.e. a new function arising from two given functions. We can also take the form of one of the functions as a monomial and product them. And we also have the notion of a composition of functions. So carrying those ideas from pre-calculus into the power series representation of nice functions, what can we do? Well, suppose that we have a nice function f, which has a power series representation, and that representation holds over some interval capital I. Suppose the same is true for some g. Okay, well, how do we distinguish the power series representations of f and g? That's entirely given by the coefficients cn, defining the f, and the coefficients dn, defining the g. Good. Now, this theorem is taking m to be an integer and b a real number. The first one is simply saying, well, if we were to take the respective summands and add or subtract them, what power series would that produce? And it's exactly the sum or difference of the f and g's. Where is this valid? This is valid in the original interval, capital I. What if we were to take, let's look at the f, each summand and multiply it by a constant times the variable of input x raised to some fixed power, m, that we would produce the series given by f multiplied by that constant b multiplied by x raised to the m. Good. And then if we were to take the x's given by f and swap them out for b times x to the m, so note that we have cn, there's a cn here, x raised to the n, and then for x, swap it out with the form of bx to the m, quantity to the n. Then what does that do in terms of the f? That's simply taking the original input x and swapping it out for this new form. The caveat being that interval I still governs. So if you manipulate the inputs, those inputs can be manipulated to any form that you like, but that their values must still reside within I. So we'll see an example of that pretty soon. First, let's do the proof, and we're just going to do the proof of statement 1. Let's consider this right-hand side, f plus g or f minus g, either one. F is given by a power series in C's, g is given by a power series in D's. These are power series, so they're infinite series. Let's do nth partial sums of each of them. Use capital S as the nth partial sum for the f. Use capital T as the nth partial sum for the g's. Knowing that we want to come up with the sum of f and g, let's take the sum of these respective nth partial sums. If we do that, then they each represent a finite number of terms. We can rearrange to our heart's content. These are just finitely many terms, and we can rearrange it such that corresponding summands are added or subtracted. And then each of those sums or differences are added together. All right, so, or in other words, this is just a property of summation that we've seen in an earlier video. Next, let's throw a limit on each side. If we throw a limit on the left-hand side, we're taking a limit as that upper capital N goes out to infinity. Throw a limit on the right-hand side. Well, that's a limit of two quantities that depend on n. We can distribute the limit onto each of those summands thanks to properties of limits. All right, and then that's it. We're done. As the nth partial sum given by s's will limit to the power series of f. The limit of partial sums capital T will limit to g. Therefore, the right-hand side is f plus or minus g, the sum or difference of f and g. And then the left-hand side, by definition, is the power series, note the infinity in the numerator, with summands as expressed. All right, so that's the proof of the first statement. Let's do an example using this theorem. All right, so here's the statement of the theorem again, and here is a statement for an example. Okay, so what's going on? Well, note that we want to deal with an f and a g. So suppose that we have an f and we have a g. The f is a power series which is determined by a sequence of cn's, and that the power series represents some function f if the input x's are taken from an open interval, -2 to +2. Likewise, we have a second power series given by a sequence of dn's, where the power series represents a finite number, provided that the value of x is taken between -3 and 3. So the first question is, what if we were to determine a power series where the corresponding sequence is the difference of cn's and dn's? By the theorem, we use statement 1 that we get that this expression will simply be the sum or difference of the functions f and g. But the question is, where is this valid? And it's valid over I. So that means that I, capital I, must apply to both the f and the g. Well, the f has an interval negative 2 to 2, whereas the g has an interval, negative 3 to 3. You take the intersection of those two, in other words, you take the smaller of these two, such that they overlap, and negative 2 to 2 is contained within negative 3 to 3. Thus, the first one converges on negative 2 to 2. All right, pretty straightforward. On the next one, take a look. Which of these three statements is going to apply? Well, we're not dealing with one, a sum or difference. We're not dealing with two, since we need a constant and then the variable to a fixed integer. We're dealing with condition 3. In other words, we can bring the 2, which is a base with power n, and x is also a base with power n. We can combine that and write that down as 2x quantity to the n. Thus, we're taking our b value as 2, our m value as 0, and our m value is 1, so there's no change. So we need 2x, and this is the CNs, and the CNs determine a power series which is valid on negative 2 to 2. That's for input x's, so that's these input x's. But for our power series, we need 2 x's, twice x, to lie in between negative 2 and 2. In order to recover our x, we would divide by 2 and thus get negative 1 up to 1. Nice. Okay, so that's this theorem. And then here's an example for you to apply. We're given our function f, power series representation, the interval of convergence. What if we manipulated things such that we're not just taking x to the n, but we're taking x over 2 to the n? How does that affect the interval of convergence? Good. All right, so that's the notion of combining power series. Now let's actually look at producing a new power series. Recall that we have, thanks to the geometric series, simple substitutions in order to take an algebraic function and write it down as a power series. Well, suppose that we take an f and a g. And suppose that we want to sum the two functions, the f plus the g. Then we can easily work with the algebraic representation of each of the f and g. We can perform algebra. This is a sum of two rational functions, differing denominators, force them to have a common denominator, do a little bit of simplification, and come up with the sum function as it can be expressed algebraically as 2 over 1 minus x squared. All right, so we have options. This actually, we could again use the power series as a geometric series to come up with its form. Alternatively, we can use the theorem that we've just looked at to say that if we have one power series and another power series, and we want to sum the two power series, then we can simply look at the sum of the respective summands. All right, so x to the n combined with negative 1 to the n, x to the n. Then this is going to either cancel out or double up. Let's first pull off x to the n. And then this quantity negative 1 to the n will either be negative 1, leading to 0, that term goes away, or 1 plus 1, leading to 2. So instead of trying to only express, Well, what we're doing is we're saying that only the even powered, if you think about when is -1, +1, that means that the n value must be an even power. And we can express the even powers on our x as twice n. And then we've changed our coefficient to 2. So this is only summing up even powered expressions on x. Good. And then coming back to this notion of, well, we have this algebraic expression, which we can plug into the formula for the geometric series. That would mean that our very first term a would be 2, and that the common ratio r would be x squared. Doing so, that we would lead to this geometric series. We don't want to term it a geometric, we want to term it as a power series, of course, because there is an x involved. Okay, so your turn. Find the power series representation for these 3 functions. The third one, give you a little hint. Try using partial fractions. Good. A few more. On these, make sure that you find the interval of convergence. This is using that theorem that we had. And so that's finding functions from power series. And that was adding or subtracting, but there is also a basic algebraic operation of multiplication. What if we have one power series and we want to multiply it with a second power series? This goes under the term, phrase, a Cauchy product. Taking one power series, product with another power series is a Cauchy product. We'll assume that both the f and the g have an interval of convergence, capital I. So we want to produce a Cauchy product. A Cauchy product is the product of one power series and another power series, or f product g. And we want that to be a power series itself. To have a power series, you're going to come up with coefficients, sequence of coefficients. The e sub n is the coefficient to x raised to the power n. Producing a power n, you want to think of all the way that you can take 2 integers. 0 plus n is n, 1 plus n minus 1 is n, all the various ways in which you can take 2 integers and sum up to n. And that would be looking at c coefficients from c and coefficients d and producting them and then summing all those up. All right, let's do an example of this. It'll help explain and understand the theorem. Okay, so take an f, 1 over 1 minus x, and a g, 1 over 1 plus x. Familiar power series. And we want to form the Cauchy product, f product g. All right. Well, let's work slowly through this. Here's f, and here's g, and we're taking the product. Good enough. Let's work slowly through this. So let's expand each of these out. So the f is summing up powers on x. Here's x to the 0, x to the 1, and so forth. The g is summing up powers of x, but we're alternating. Beginning at n equals 0, that means -1 to the 0 is positive. We begin positive, and then alternate negative, positive, and so forth. Okay, so by writing out the form of each of these, not using the summation notation, but writing them out to look at the pattern, we see that what we want to do, one way to approach this, is to take the very first term in the first factor and multiply it with everything representing the second factor. So that's what we have here. And then repeat. Now use the second term and multiply it with the second factor. So here we have x, the second term in the first series, multiplied by the second series. And repeat. And so on and so forth. All right. The series representing f is an infinite series. We use the plus ... the ellipses to represent. You do that until you've used all the terms. There are an infinite number of terms. We would not be able to finish this operation in any given finite time. So our hope then is to just produce the first few terms. Okay. So how can we proceed? Well, we can do something very obvious. We can distribute out the monomials onto the series. So that's pretty easy to do. If you take 1 times the series, you just get back the series. If you take x times the series, you look at each term in the series and you bump up the power on x by 1. 1 is x to the 0, that goes to x to the 1. X is x to the power 1, that goes to x squared, and so forth. Likewise, when you look at x squared and distribute it out, you're going to get x squared minus x cubed. You just take each power and bump it by 2. And I've done the next line where I've distributed x to the power 3 onto the power series representing g. Okay. So let's see. Looking at all of these terms, let's collect all of the constants. Well, there's only one constant, so that's easy to do. Nice. How about we next look at all of the linear terms? Well, these are only going to be the 2 linear terms, and they cancel out. Nice. Don't have to write anything down. Move on to degree 2 terms. We only have these 3 degree 2 terms. 2 of them appear with positive 1 as coefficient, and 1 appears with negative 1 as a coefficient, leaving us with a single x to the power 2. Cubic terms, we have these 4. We're then going to produce a cancellation. Don't have to write anything down. Degree 4, the ones that we've explicitly written down, we say that there are 4 of them. They will cancel out. But there's also one that we didn't write down, and it will have a positive coefficient. So we write down plus x to the 4th. And then we continue in this pattern until we have written down as many terms as we like. Here, this is the first 3 non-zero terms, and notice that we went out to power 4. Very nice. And again, this is called a Cauchy product. Now, we've seen this before. We know how to multiply the f and the g. We know that 1 times 1 is 1, and 1 minus x product, the sum of 1 and x is going to lead to 1 minus x squared. We can then use a geometric series to identify the power series representation of this function. The a value is 1, and the r value is x squared. Beautiful. Your turn. Here's a function f, here's a function g. Produce the first 3 non-zero terms of their Cauchy product. So that is multiplying power series. In other words, computing a Cauchy product. This is calculus. How about differentiating and integrating? All right. Infinity is bizarre. Where have we seen that? Well, we saw that in the Riemann rearrangement theorem. We took the alternating harmonic, we took it on supposition that it's equal to ln of 2, so that's up here, ln of 2, we rearranged the terms, and we see that we're getting, by multiplying 1/2, then we interjected a 0. And then when we look term by term, we produce the bottom line, summing those up, and we know that 1 plus 1/2 is 3/2. Yet the rearrangement, if we look on this left-hand side, the rearrangement, we are producing exactly all of the original terms. So that if we take them in one order, we'll produce ln of 2, or if we take them in the order that we arrived at, we'd get 3/2 ln of 2. So this obviously cannot happen in the case of rearranging finitely many summands, but it does if you have infinite summands. So this notion is captured in terming a convergent series as either conditionally convergent or absolutely convergent. Conditional convergence is weak in that it is vulnerable to this rearrangement. And in fact, you can produce any right-hand side that you like through a choice rearrangement. Absolute convergence doesn't suffer from that. And thus, we want to look at power series, which depends on a radius of convergence. The radius is how far can you stray away from the center A. That capital R is computed using the ratio test, and the ratio test gives absolute convergence. And in our producing of it, we get absolute convergence on this open interval, which means that rearrangements are no problem whatsoever. And if rearrangements aren't any difficulty at all, then throwing a derivative on the entire expression will be the same thing as throwing a derivative on each of the summands and then bringing everything back together. So that if we have a power series with center A, radius of convergence capital R, that we have an interval, and over this interval we can compute out the derivative of this power series by simply differentiating term by term. We know how to differentiate. The power n comes down, and we decrement the power. And then this derivative will itself be represented in a power series, and it inherits the exact same interval of convergence. All right, so let's go ahead and do an example of that. Let's come back to our trusty 1 over 1 minus x, and then term by term differentiate. Okay, so the f, note that the f is centered at 0, and that the radius of convergence is 1. Okay, term by term differentiation means that we're going to get the n popping down and the power n decremented by 1. So that's the right-hand side. On the left-hand side, we know that we have 1 over 1 minus x. That's 1 minus x quantity to the negative 1. And when we differentiate that, a negative 1 pops down, power decrements to negative 2. But then by the chain rule, we're going to get that negative 1 we brought down cancels out. All right, so that's f prime. And then to write down f prime, and note that the index is beginning at 1. Make a big note of this. As when the index was 0, differentiating a constant, it goes to 0. We could have the n begin at 0, and then that's equally represented, that n equals 0. This term will go away. It's more convenient, however, to start at 1, so that we can do a change of index, introduce a new variable of index, k. Let k equal n minus 1. So if we have n minus 1, that's going to be represented as just a k in the new variable. By adding 1 to both sides, we can come up with an expression for n as k plus 1. so that if we see n, we can swap it out with k plus 1. And if the index under the original variable n starts at 1, then for n equaling 1, k must be 0. Good. In terms of the interval of convergence, we know that it's also going to be -1 to 1. We have to double check that. That if we plug in -1, then we're summing up terms that get larger and larger. If we plug in +1, we're summing up terms that get larger and larger. In both situations, the divergence test will tell us that the series diverges. Nice. All right. So the last comment was, what about the endpoints? So this is the caution. We have this theorem, and this theorem tells us nothing about the endpoints. We can start with a power series which converges at the endpoints, but if we differentiate, we have no idea what's going to happen at the endpoints, that we have to test the endpoints. All right, so this is differentiation. Note that we're also able to integrate term by term. Let's make that statement here. Update this theorem from differentiation to integration. Note that what we're doing is we're integrating term by term. So there are going to be an infinite number of constants of integration. Easier way to think about that is the very first one produces a constant. All the others are set equal to 0. Right. So what we get is that if this power series represents a nice function f, which has convergence on this interval of radius r about a, that we can integrate that function f, and that this is an indefinite integral, so we'll pick up a constant of integration. Think of antiderivatives. And we'll pick up some function represented by this power series. What is the sequence defining the power series? The sequence is Cn over n plus 1 as coefficients to x's to the power n plus 1. All right, let's take a look at an example. So we want to do term by term integration. Let's take f to be 1 over 1 plus x. This will be an alternating series. And we want to term by term integrate and find the interval of convergence. Okay, so this f has interval of convergence, open interval, -1 to 1. How about its integral? So let's integrate. Let's do the right-hand side. We're going to pick up a constant of integration. The power n increments to n plus 1, and we divide through by that new power. Good. So that's the right-hand side, term by term integrating. Now let's look on the left-hand side. Well, this is essentially 1 over the variable, which is ln. Thanks to a u substitution, left-hand side, we can write it down as ln of 1 plus x. Oh, very nice. Okay. Now, we have this constant of integration. Can we do anything about it? Yes, we can. We can plug in x equals 0. If we plug in x equals 0, the entire series will evaluate to 0. Plug in x equals 0 on the left and get ln of 1. ln of 1 is 0. Thus, the constant c is 0. Pretty nice. Okay, so how about the last part, determining the interval of convergence? Well, here's the answer. It's open at -1, but closed at 1. How can we be assured of that? Well, we verify. We let x equal -1. At -1, 1 plus 1 is 0. ln of 0 doesn't exist, so that's not looking too good. Well, double check on the right-hand side. What would we have? plugging in x equals -1, you get -1 to the n plus 1. You can rewrite that as -1 to the n. Something times itself, positive or negative, is going to be positive. And then you're left with the -1 to the power 1. But this is essentially the harmonic series, and the harmonic series diverges. Thus, -1 is not included. Good. How about the other side? How about at +1? Well, that's going to give us ln of 2, ln of 2. And then on the right-hand side, we'd have +1 to some power is just +1. And note that if we make an adjustment for the starting point of the index variable, that this is exactly the alternating harmonic series. So we finally established that the alternating harmonic series has a value ln of 2. Yay! Very nice. Okay, and then in terms of this example, it's showing that +1 is included in the interval of convergence. Your turn. Term by term differentiate, then find the interval of convergence for the given power series, and also the power series obtained by term differentiation. Good. So that was arctan. Here is ln of 1 plus x. That's the one that we just worked with. Now integrate that once more. State interval of convergence for what you're beginning with and then what you end up with. And likewise, integrate and evaluate both sides at x equals 0 like we did in the example to determine the constant of integration. And then further, take the limit on the variable x as x goes to -1 from above in order to produce a value for this right-hand side for this expression. And that's a challenge problem. Here's another challenge problem. Prove that the power series representation of a function is unique, and this you can reference the textbook. And then a last assignment, where the power series centered at 0 that represents each function. And so this is just going back and looking at our examples and manipulating. Very nice. So we've done quite a bit. You've expanded the usefulness and application and prowess of power series. It's the end of our video. Thank you so much for watching. Please like if you find the video useful, and I will see you on the next one.